In this video, we're going to focus on acid-base reactions. For the most part, predicting the reagents that you need to drive the reaction to the right. In order to predict the appropriate reagents, you need to be familiar with the pKa values of certain acids. So for this reaction, we have ethanol, and we want to deprotonate it. We want to remove the hydrogen to create ethoxide. And we want to use a strong enough base to drive the reaction to the right. So let's make a list of some bases that we know. Hydroxide is a common strong base that we could use. The conjugate acid of hydroxide is water. Now we need to be familiar with the pKa of the conjugate acid. The pKa for water is 15.7. Another base that we could use is the amide ion, NH2-. The pKa for the conjugate acid, you may want to write these down, is somewhere between 35 and 38. But just to keep things simple, let's go with 35. Now there's some other bases that we could use too. For instance, we could use ethoxide. This might be useful if the solvent is not as polar as water. And the pKa of the conjugate acid is 15.9. We can add more later, but let's stick with this. Now let's say if we were to use hydroxide. Hydroxide could remove hydrogen from ethanol, creating ethoxide. But let's talk about the position of equilibrium here. The pKa of ethanol is 15.9. The pKa of water is 15.7. The position of equilibrium is going to favor the side with the weaker acid. This is the acid on the left, and this is the conjugate acid on the right. The weaker acid is the one with their higher pKa value. So the position of equilibrium will be slightly to the left. They're almost equal because these two values are almost equal. So this reaction is like almost 50-50, but it favors the left side a little bit more because this is a weaker acid. So hydroxide won't be a good base to use here because it won't drive the reaction to completion. Only almost half of it will be ethoxide. So we need a stronger base for this reaction. We want to choose a base whose conjugate acid has a pKa value that is at least 2 units greater than the pKa of the acid that we wanted to protonate. So in this case, the amide ion will be a good choice. So let's put NH2- here. NH2- is strong enough to remove the hydrogen from the alcohol, giving us ethoxide plus the conjugate acid NH3. So now let's compare the pKa of the original acid, which is 15.9, to the pKa of the conjugate acid, which is about 35. The reaction is going to shift in the direction towards the weaker acid, towards the acid with the higher pKa value. So it's going to definitely shift to the right because the pKa of ammonia is much higher than ethanol. So that's how you can choose a strong enough base. You want to choose a base where the conjugate acid of that base has a pKa of 2 or more units higher than the original acid. If it's 1 unit higher, 10 to the 1 power is 10. That means the ratio of products to reactants will be 10 to 1. So if you pick a base where the conjugate acid has a pKa of 1 unit or more, the yield will be like 90%. 90% products, 10% reactants. But if the pKa is 2 units or more, 10 squared is 100. So the ratio of products to reactants will be like 100 to 1, which is much better. I'm thinking of the Henderson-Hasselbalch buffer equation. When the pKa is 2, when you have that difference, the ratio of products to reactants is 100 to 1. So 99% will be like in the product form, 1% will be in the reactant form. a 99% yield is pretty good. So at least you want to choose a base whose conjugate acid has a pK value that's 2 or more units greater than the original acid. So that's how you can tell which base to use. So let's try another example. Let's use phenol. What base can we use to deprotonate phenol, creating phenoxide? Now, phenol has a pKa of approximately around 10. So we need to pick a base whose conjugate acid is 12 or more. In this case, we don't need to use this powerful base amide. Hydroxide could work, or even ethoxide. Now, if water is the solvent, I would use hydroxide. But if your solvent is not very polar, let's say if it's more on the nonpolar side, I would use ethoxide and ethanol. But for this, we could use water as a solvent and hydroxide as the base. So when hydroxide removes the hydrogen, it's going to create water as the conjugate acid. The pK of water is 15.7. So the position of equilibrium will favor the side with the weaker acid, and that's the side with the higher pKa value. So it's going to be far to the right. And so that's how you can determine which base to use. You just need to compare the pKa of the conjugate acid to the pKa of the acid that you want to deprotonate. And you just want to make sure that this is at least 2 units or more than the pKa of the original acid. Now let's try another example. So let's say if we have methylacetylene, you could also call this propine, and we want to deprotonate the alkyne. We want to remove the hydrogen. So first, we need to analyze the pKa of alkyne. The pKa of this hydrogen is 25. So we need to look for a base whose conjugate acid has a pKa that's greater than 25. And so NH3 is 35. Therefore, we want to use NH2 minus to remove that hydrogen. Hydroxide is not strong enough. The pKa of water doesn't exceed the pKa of the terminal alkyne. The pKa of ammonia does. So we need to use NH2 minus to remove that terminal hydrogen. So far, we've considered examples where we would use a strong base to deprotonate an acid. But what about using a strong acid to protonate a base? In this case, let's say if we want to protonate an alcohol to create this product. What type of acid do we need to get the job done? To really drive the reaction to the right. So some acids that we could use are HCl, HBr, HI, sulfuric acid. And you need to know the pKa values for these acids. According to my textbook, the pKa for HCl is 7. For HBr, actually this is -7, not +7. For HBr, I have -9, -10 for HI. And for sulfuric acid, I had to look it up, but based on its one website, I saw a value for -10 for that. Now, in order to determine which acid we need to use, we need to compare the pKa of the acid with the pKa of the conjugate acid. The pKa of a protonated alcohol is between -2 and -3. So for this one, it's like -2.5. So we need to choose an acid with a pKa that is at least 2 units lower than -2.5. And any one of these strong acids will do. So we could simply use hydrochloric acid. So let's write the mechanism for this reaction. So here's HCl. So we're going to draw an arrow from the base to the acid, and then the bond between H and Cl will break. Those electrons will go back to Cl. So we get the conjugate base chloride. So if we were to compare the pKa of the conjugate acid, which is -2.5, to the pKa of the acid on the left, which is HCl, we can see that HCl has a pKa that's more than 2 units less than this alcohol. So the reaction is going to shift to the side with the higher pKa value. Negative 2.5 is higher than negative 7. It's more than 2 units away. So it's greatly going to drive the reaction to the right. Now let's use a different acid. Let's say we have a carboxylic acid and we wish to protonate it. We wish to convert it to this form. Which acid should we use? By the way, the pKa of a protonated carboxylic acid is negative 6. Now, if we were to use HCl, HCl is a stronger acid than this one. The reaction will still go to the right, but we're talking about yields of 90% as opposed to like 99% or more. So it's better to use a stronger acid. These two, they only differ by 1 unit. So I would recommend using HBr. HBr is stronger than HCl. So with a pKa of negative 9, this is more than 2 units apart. Now, equilibrium is going to shift to the side with the weaker acid. That is the acid with the higher pKa. Negative 6 is 3 units higher than negative 9. So it's going to shift far to the right. The other product will be bromide. And to show the mechanism, all we need to do is draw an arrow from the lone pair of the oxygen that's going to acquire the hydrogen. That lone pair is going to go from the oxygen to the hydrogen, and then the bond between H and Br is going to break. Those electrons go back to Br. So anytime you wish to protonate a molecule to create a conjugate acid, you want to choose a strong acid that has a lower pKa than the pKa of the conjugate acid. And you want this pKa to be 2 or more units less than this number. Now for this one, we need to predict the reactant and reagents needed to produce the products on the right side of the equation. And we want to choose the reagents that will favor the product side of the reaction. Now if we look at the products, notice that these elements have negative charges. Typically, that means that the starting material were neutral, which means we need a base to deprotonate the starting material to make those negatively charged ions. So to find the starting material, simply add a hydrogen to those negatively charged ions. So this is just going to be SH, and this is going to be OH. So now we need to consider the pKa values. The pKa value for this diol is about 10, and for a secondary alcohol in a ring, it could be anywhere from 16 to 18. So to deprotonate this diol, we need a base whose conjugate acid has a pKa that's greater than 10. Hydroxide will do, or ethoxide. For this one, I'm going to use ethoxide because of this alkane chain here. Ethoxide in ethanol will dissolve better in a less polar solvent than water. So the conjugate acid of this will be ethanol. When ethoxide removes a proton, it becomes ethanol. So the pKa of ethanol is 15.9. It's much higher than the thiol. So the reaction is going to shift to the side with the weaker acid, that is with the acid with the higher pKa value. So it's going to shift to the right. So ethoxide is strong enough to remove the hydrogen from thiol. Now for cyclohexanol, we don't want to use ethoxide because 15.9 is not much, it's not larger than 16 to 18. So we need to use something stronger. Now we could use NH2- based on the options that we have. And this is definitely strong enough to remove an H from an oxygen. The pKa of ammonia is somewhere between 35 to 38. It's much higher than 16 to 18. So the reaction is going to be shifted far to the right. Now let's try some other examples. So let's say if we want to make the protonated form of pyridine. What reagents do you need, and what's the starting material? And also, let's say if we want to make this product as well. What do we need? Well, in this case, the products have a positive charge, so we need to add an acid to the original reactant. To find the original reactant, remove a hydrogen. Last time we added a hydrogen, this time we're going to remove one. So the starting material is going to be pyridine. And if we take away a hydrogen from the nitrogen, the starting material will be a primary amine. So now we just got to add an acid to go from the reactant to the product. So first we need to pay attention to the pKa of the conjugate acid. The pKa of the protonated form of pyridine, that's around 5.2. For a protonated amine, it's around 9 to 10. So in order to make this conjugate acid, we need to use an acid with a pKa that is less than 5.2. Ideally, 2 units or less than 5.2. So when I say that, I mean something that's like 3.2 or lower. So what acid can we use that has a pKa of 3 or less? Well, we don't want to use a carboxylic acid because the pKa for that's like 4.76. It's too close to 5.2. HF, I think, has like a pKa of like 3 to 4, so we don't really want to use HF. So in this case, we could just use HCl. HCl is, more than enough to get the job done, but it's a common acid and it's going to work. So if you were to use HCl, this is definitely going to get the job done. So 5.2 to -7, it's a huge difference. The reaction is definitely going to go well to the right. Now for the next one, we could use HCl as well, but that might be too much. We don't need to use a strong acid. We could use a weak acid like a carboxylic acid such as acetic acid. The pKa of acetic acid is 4.76. And the reaction is going to shift to the side with the higher pKa or the weaker conjugate acid. And so 4.76 is more than 2 units away from 9 to 10. So this is definitely more than enough to drive the reaction to the right. The byproduct is going to be acetate. So that's how you can predict the reactant and the appropriate reagents that you need to drive the reaction forward. Now let's summarize what we've learned today. When predicting the reactant, if you see a product with a positive charge, simply remove a hydrogen to write the structure of the reactant. In the last two problems, where we had a negative charge, we had to add a hydrogen to get the reactant. Now, when making the conjugate acid, you need to choose an acid whose pKa is lower than the pKa of the conjugate acid. And you want the difference to be at least 2 units or more. So if the pKa of your acid is 4, if the pKa of the conjugate acid is 4, the acid that you're going to use as a reagent, you want it to be 2 or less. 2, 1, 0, something less than 2. Now, when using a base to deprotonate an acid, like we did at the very beginning of this video, you want to pick a base whose conjugate acid has a pKa that is 2 or more units higher than the pKa of the original acid from which you want to deprotonate from. So that's a summary of what we learned today. So now you know how to choose the reactant. You just got to either add or remove a hydrogen to get the reactant, and you now know how to choose the appropriate reagent. If you need to use an acid, make sure the acid has a lower pKa than the conjugate acid. And if you need to choose a base, make sure that the conjugate acid of that base has a higher pKa than the acid from which you want to deprotonate from. So that's it for this video. Thanks again for watching.